right, let's pick it up where we left off. We did these examples. Where are we going to go next? So we're going to recognize, hey, now that we're thinking of the derivative f prime of x as a function has a graph, since we can do it for any x value. So what we're going to do, we're going to sketch the graph of f prime of x based on the graph of the original function f of x. And even doing this, I think it'll help us even build an intuition for what's happening with the derivative and how it's related graphically, what's happening in the original graph and what that tells us about derivatives at that moment. So this will be a good concept builder at the same time as an example. So first one we're given is this graph here. It's kind of got this W shape. That is f of x. We're going to be able to sketch f prime of x just from that. And notice, we're not given any numbers on the x and y axes, because we're just kind of going to do this a little bit more generally. And that's going to be much simpler for our experience right now. Okay, and building this. All right, let me switch over. Sketch f prime of x. So f of x, kind of draw that again. Had that W shape, right? So it kind of came down and then came back up, down. It was nice and symmetrical. There's f of x. Here's what we want to do. We want to notice kind of some of the features of f of x, and that will give us a starting point on how to graph f prime. Let me have kind of a similar xy plane down here where we can graph f prime of x. So what can we notice from f of x? Notice the peaks of these bumps and the valleys. What's happening with the derivative whenever we meet with kind of the bottom of that valley or the peak? If you were to draw the tangent line, and we mentioned this a moment ago, the tangent lines there would be horizontal. Well, what's the slope of a horizontal line? 0. If the slopes of the tangent lines are 0, then on the graph of f prime, these would all be located on the axis. F prime of x is graphing the value of the slopes. Well, the value of the slope, 0, 0, 0, so 0, 0, and 0. Okay. Now let's look at the other pieces of the graph. So here, and we always look from left to right. So here we're thinking, any tangent lines here would be doing something like that. Tangent lines here would be doing this. Tangent lines here, tangent lines here. So generally, kind of what's true in each of these zones. So in this portion where it's going down, where the graph is decreasing, all of the tangent lines have a negative slope. M is less than 0. Then it turns and it starts going up. Well, these tangent lines have a positive slope. And then back to negative, and then back to positive. So when we graph the derivative or in the sketch, we need negative values below the axis. Then they'll switch to positive values, then back to negative, then back to positive. So they're negative here, but they are headed towards 0. So kind of think like they're more negative, but they're becoming less negative. So the slopes, the further out we go to the left, that slope is more negative than it is as we start moving over. And as we start getting close to that bottom, the slopes are still negative, but they're they're less negative, right? So it's getting closer. And by the time we actually get to the very bottom, it's at 0. As we keep moving on, the slopes slowly become more and more positive, but then they start getting less positive as we get to the top. So it becomes more positive, but then at some point they start becoming less positive. And by the time we get here, we're back to 0. Then the slopes start to become just a little bit negative, then more negative, and then less and less and less negative. Something like that. A little bit negative, more negative, but then they start leveling back out again, getting less negative. And then finally, after we pass this point, they're getting positive, the tangent lines, and they're getting more and more and more positive, and they're just getting more and more positive as we go on. So there's a sketch of f prime of x. All right. It takes a moment to sink in. This is not, I don't expect people to pick this up immediately. Sketching the graph for the values of slopes is not, that's a strange thing to do. That takes some getting used to. Okay, but for now, let's move on. There's another example. Go back to the lecture. So we just did that one. Let's try it again for this. We're going to have some of the same features with like, where is the tangent line positive and where is it negative? This one though has this interesting feature right there at the origin when those kind of where that comes together. It almost looks like the function is bouncing, kind of bouncing, coming in, bouncing, and then bouncing away. Let's see what that would look like. Try and do that here. So it's coming in and it's hitting, and then it's going away kind of the same way it came in. Okay. So that's f of x. Let me graph this here. Something like that. Give yourself a little bit more space on the negative side than what is in that original graph. Okay, how is this going to work? Let's start with this first piece. So it's coming in and tangent lines are negative, right? And they're becoming more negative. Oh, that's interesting. They're negative, but they're getting more negative. Okay, so they're negative. Maybe I'll put it like right in there, but then they're getting more negative. It's going down. All of a sudden, where you hit this point, if you're thinking of it from the left, the tangent line's like doing that. But then immediately following, the tangent lines are positive. And they're very positive right at first, but then they start to get less positive. So very positive and then less positive, maybe something like this. What's going on here? Right at the moment where that happens, let me erase my tangent lines. We give a feature like that a name. That is called a cusp in the graph. I kind of like that word cusp, just kind of the way that it makes your tongue hit the roof of your mouth or something, just the way that sounds, it sounds sharp, right? The cusp. There's this kind of almost like this clicking noise kind of at the very end of saying it, cusp. Because it's this sharp point. When that happens, you get something like this in the derivative. You get like this jump. So on the left side, the tangent line is very negative. And then immediately as you're moving along, it's very positive. Right at the moment itself, right at the point, there is no derivative. Both of these are open circles. At the moment of that cusp, we'd say there is no tangent line. We say there is no tangent line because the tangent line from the left does not line up with the tangent line on the right. And very much like a limit, the left side, what's happening on the left side needs to be the same as what's happening on the right side. Obviously, derivatives are based on limits. They involve a limit. So what's happening on the left has to equate with what's happening on the right. And that is not true at a cusp. They're going in two different, it's almost like, you know, at the same point, you have two different tangent lines. You're like, well, which one is it? And well, the answer is it's neither. They have to agree. And it makes sense in the graph. It's getting more and more negative on one side. It's getting more, on the other side, it starts off very positive and then getting less positive. So you have this big leap in between. So at that one point itself, there is no derivative. Like I said, they're both open circles. Okay, kind of a strange thing. Totally get it. But there you go. And that's our graph. That's all there is to it. That's all there is to it. All right. Let's go back to the lecture. We did it. We sketched the graphs of our W, kind of much nicer. It's almost like smooth, right? It comes down, it levels off slowly, tops out slowly, comes back down, right? And so everything worked with our derivative sketch. But here where we have that sharp angle, that cusp, the derivative did not exist there. Very nice. Let's move on. This is related to that conversation. F of x is said to be differentiable at A if f prime of A exists. So we use this word differentiable. I'm not really sure why we use the word differentiable if the derivative exists. You would think we would use the word derivable, right? Derivative means it can be derived, but we don't use the word derivable. We use the word differentiable. All that means is the derivative at that value A does exist. So that just kind of brings up the question, well, what would cause f prime of A to not be differentiable at A? In other words, what would cause f prime of A to not exist? Well, we've certainly seen a few cases and even one just now. What would cause f prime of A to not be differentiable? You know, kind of going back further to our conversation on limits. Well, if f of x has a jump, a hole, or a vertical asymptote at A, then f prime of A is not going to exist. We even saw a case with a vertical asymptote with an example earlier in this section with g of x equals 1 minus x over 1 plus x, had a vertical asymptote at -1. So obviously the derivative is not going to exist there. But also if your function had a jump or a hole. What we just talked about was the cusp. So here it's not a jump, it's not a hole, it's not an asymptote, it's just this sharp angle. So in one sense, the function is doing everything just fine. But when it comes to a derivative, you know, kind of the idea is the two sides of the cusp disagree about what the tangent line is. And if that's the case, then we just say, well, then there is no tangent line at a cusp. And so then, you know, that would mean that that the derivative f prime of A would not exist there. There actually is one more case where your kind of an unusual thing where your derivative would not exist. And that's if f of x has a vertical tangent line at A. Let me draw you a sketch of a vertical tangent line. So something where let's do a good example is something like f of x equals the cube root of x. If you were to graph the cube root, it would come in, approach 0, kind of start to level out like that. And then it would have that mirror image and keep going. There's cube root of x. I might not have done the best job at drawing it, but right here at the origin, think of the tangent lines. The tangent lines are positive. The tangent lines are getting more positive. Right at this moment, the tangent line is perfectly vertical. Then as you keep going, the tangent lines start to level out again. But right there at the origin, just for an instant, the function is moving perfectly vertical, not enough to violate the vertical line test, which is crazy, because it then immediately starts to curve back the other way. If your tangent line is vertical, obviously m is undefined at that vertical tangent line, and so your derivative does not exist. Maybe I can graph this. Graph a cube. I think I just have to say x to the 1/3. There it is. That's a much better graph. And now, yeah, you can really see it there at the origin or cube root. That tangent line is perfectly vertical just for an instant. So there you go. So a vertical tangent line at A would cause your function to not be differentiable either. Last idea in the section, just kind of tying it all together. There's this theorem. If f of x is differentiable at A, then f of x is continuous at A. Think, okay, would that follow? If it's differentiable, does that mean it has to be continuous? You're like, well, yeah, if a derivative exists, then f of x would have to be continuous there, right? Because if it wasn't continuous, if there's like a jump or a hole or something, then that wouldn't be differentiable. So if we know that there's a derivative, if we know that there is a tangent line, then there could not have been any holes or jumps or vertical asymptotes, right? Maybe this even makes it a little bit easier. If you're, what do these things mean kind of in more common terms to us right now? If f prime of A exists, then we know, continuity, we know that the limit of f of x as x approaches A would have to equal f of A. There can't be a hole or a jump or a vertical asymptote. Okay. Here's kind of an interesting question that often, just the logic of it, we can get confused. Is the converse also true? It's easy to look at a theorem and be like, yeah, that makes sense, right? If it's differentiable, then it must be continuous. And we can mistakenly sometimes reverse that and say to ourselves, well, if it's continuous, then it must be differentiable too. We can almost like say that these things are almost like equivalent. Like if it's differentiable, then it's continuous. Or it's like that, if it's differentiable, that's the same as being continuous. And that's not necessarily the case. We call it the converse if you take a class in logic. if you reverse the if and the then, would that still work? So here it is. If f of x is continuous at a, does that imply that it's differentiable? Is it guaranteed to be differentiable? And you're like, well, if it's continuous, there's no jump, there's no hole, there's no asymptote. What could go wrong? The truth is no. Even if you're continuous, that does not guarantee that the derivative is going to exist. And we actually saw a couple of examples. We talked about them already in the section that, so the answer is no, right? What if there's a cusp? A cusp is continuous. There's just that sharp point, but that's perfectly okay for continuity, right? You come to that sharp angle, but there's no derivative there. It's not differentiable. And the vertical tangent line, vertical tangent line is perfectly continuous, but because the tangent line is vertical, there's no derivative. So kind of interesting that it doesn't work the other way. Just something to be aware of. All right, guys, that is it for this section. Let me put the camera. That's 2.8. That's chapter 2.